Hey everyone, welcome to this explainer. You know that feeling when you ask an AI model a question and it spits out a completely hallucinated, totally off-the-wall answer? Yeah, we've all been there. Ultimately, an AI's final output is really only as good as the data it was fed during training. But how do you actually prove where that data came from? Well, today we are decoding the Codatta data assembly and lineage framework. We're going to look at exactly how Codatta takes raw, messy data points and transforms them into trustworthy, reproducible datasets with absolutely crystal clear provenance.
To really wrap our heads around Codatta's data architecture, I actually want you to think back to chemistry class for a second. We have to start at the absolute microscopic level. In this framework, they use something called contribution fingerprints, or CFs for short. And these CFs, they are the atoms. Every single piece of data is treated like a fundamental, indivisible element. By looking at data through this chemical lens, it becomes super easy to see how simple, tiny elements can snap together to create some highly complex, incredibly valuable structures. So here is our roadmap for today's explainer. First, we'll look at the atoms of data, then assembling assets and datasets. Third, we'll map out the map of lineage, and finally, we'll wrap up with versioning and invariance. All right, let's jump right into section 1, the atoms of data, and get a solid understanding of these contribution fingerprints. Now, the absolute golden rule of a contribution fingerprint is immutability. It's the smallest possible unit of work, and it is permanently recorded by its own unique fingerprint the exact millisecond it's created. Think of it literally like writing in permanent marker. If someone comes along later and wants to fix a typo, they don't get an eraser. They can't delete the original. Instead, they have to create a brand new fingerprint that simply references the old one. The history is never, ever erased. So, what are these atoms actually made of out in the wild? Well, there are basically three kinds of atomic contributions. First up is the sample. This is your raw, original encrypted material. Maybe it's an image, a text snippet, a telemetry trace. Next, we have the label, which is just a structured claim about that sample. Think of a bounding box around a car in an image or a specific classification. And third is validation. This one is essentially a strict quality control checkpoint. Now, a validation absolutely cannot stand on its own. It's basically a reviewer coming in and saying, hey, I approve or I reject this, based entirely on the exact IDs of those previous steps. And remember, throughout this, the original sample and label stay totally unchanged. Moving right along to section 2, assembling assets in datasets. This is where we start building the molecules. As we start snapping these data atoms together, we end up with two distinct types of structures, and it's important to know the difference. You have your data asset. Think of an asset as a highly specific, reusable ingredient. It's a curated bundle of those fingerprints, like, say, a collection of lung pathology images. Then you have the dataset. This is the fully baked cake. It is the final, usage-ready version collection that's pinned down by a specific manifest. This is the actual product that AI builders are going to license and use to train their models. Now, you might be wondering, why go through all this crazy trouble to track every single tiny piece of assembly? One word: ownership. Tracking these individual components matters immensely for the human creators actually doing the work. Because the Codatta framework tracks every single atomic fingerprint, it ensures that tokenized ownership is perfectly preserved all the way up the chain. So when an AI company licenses that final dataset, the system knows exactly who contributed what and exactly who to pay. Honestly, this isn't just good bookkeeping, it's practically the foundation of a fair, functioning AI economy. Which brings us to section 3, the map of lineage, where we'll dive into provenance and diffs. So, what exactly do we mean by lineage in this framework? Simply put, it's the directed, immutable record of how artifacts relate over time. It's the map that links your starting fingerprints to your assets all the way to your final dataset versions. It is the ultimate audit trail. It completely destroys the whole black box problem of AI data because it lets anyone mathematically prove exactly what's inside a dataset, exactly why it was included based on very specific rules, and where it originally came from, right down to the specific human contributor. If we break down how this map is actually modeled, we see a really brilliant append-only system. It's basically like a super strict family tree for your data. You've got your nodes. These are the family members, so your CFs, your assets, your dataset versions. And again, nodes are never edited. Then you have your edges. These are the genetic relationships that connect the nodes together, like explicitly stating that one asset is derived from another. And finally, properties. These edges carry exact timestamps and the specific manifest rules that actually cause the data to be included in the first place. All of this brings us to a highly practical question.
Just imagine for a second you're an AI data scientist. You're debugging a model, and suddenly it's hallucinating or making weird errors. What exactly can this massive lineage map tell you about your data to help you fix it? Well, this is where the framework really flexes its muscles. You can run these core lineage queries and just ask it point blank. Hey, why was this included? Boom, it shows you the exact manifest rule. Why was this excluded? Here is the exact rule it failed. You can trace data origins all the way back to the contributor. You can instantly run a diff on 2 different versions to see exactly what assets were added or removed. But honestly, the real game changer is the impact analysis. Let's say you realize a specific label somewhere deep in your data was legally or factually wrong. The lineage map instantly and automatically tells you every single downstream asset and dataset version that is affected by that one tiny error. It's literally like finding a needle in a haystack instantly. And that takes us to our final stop, Section 4, Versioning and Invariance. Let's talk about trust and reproducibility. Codatta has a really simple but incredibly strict rule when it comes to changes. Any tweak to your inputs or your rules automatically triggers a brand new dataset version. So say you build dataset version 1. Then later on, a fingerprint is amended, or maybe you just change your filtering policy. Instead of silently editing version 1 and messing up everyone using it, the system triggers a complete reassembly based on the new parameters and publishes dataset version 2. No silent updates where data just shifts under your nose. It makes auditing incredibly simple because you are never chasing a moving target. Let's be real, human labeling isn't perfect. Mistakes happen, disputes happen. If a fingerprint has to be amended to fix a bad label, the dataset simply reassembles itself using the exact same rules. The old, flawed version remains perfectly preserved and accessible for anyone who needs to audit the history, while the active AI models simply point to the new, corrected version for future use. You get to fix the problem, but you never lose your historical audit trail. To keep this whole ecosystem from just collapsing into chaos, Codatta enforces 4 unbreakable laws of physics, or what they call invariance. First is referential integrity. Basically, no dead links. Every single entry has to resolve to a valid CF. Second is determinism. If you put in the exact same inputs and the exact same rules, you will always get the exact same dataset version and lineage out. Third, immutability. History never ever changes. And fourth, explainability. Absolutely no data is included without a specific, stated rule dictating why it's there. Because these rules are so strict, the lineage never forms broken logic loops or cycles. We've covered a lot today: the atoms, the assembly, the lineage map, and the strict invariants that hold it all together. But as we wrap up, I want to leave you with this provocative thought to chew on. We live in a world where AI models are so often criticized as unpredictable black boxes. But if you can deterministically trace every single data point back to its uneditable origin atom, how is this level of reproducible provenance going to completely revolutionize the way we build and, more importantly, trust AI development going forward? Thanks so much for joining me for this explainer. Keep learning, and I'll catch you next time.